I'll see if faculty are invited. Maybe you can come get your frustrations out on us. Just take us down, right? We left off with optimizing. I had a problem. I made up some story, whatever story I need to continue to talk about the favorite people in my life, my wife and daughter. We had labeled a play area. My daughter wanted a rectangle. My wife had bought 100 feet of fencing. We wanted to maximize the area. Problems like this happen all the time from our future business leaders. You'll want to obviously maximize the profit, minimize the cost, but we'll always be working under constraints, right? So just like when we were doing absolute max and min on an interval from A to B, that we wanted the independent variable to be on some interval. Sometimes we don't have a choice. My wife just is not going to, good morning. My wife is just not going to be free to buy any amount of fencing. That's how much she bought. And now we want to see what could LNW be to make this stuff here as large as possible, right? So we want to minimize the length. We want to maximize the area. And so we need to find what LNW to maximize the area, given that 2L plus 2W is equal to 100. I'll take any questions about that, about the formulation of the problem. You know the deal that we'll give you some story. So we'll talk about a lot of different stories. And then there'll be some thing that you're trying to maximize or minimize. The plan, of course, is to take a derivative. Once you have this function, to take a derivative, set it equal to 0, and solve, right? And given the context of the problem, there might only be one answer. So you might not have to use a derivative test, right? Sometimes you might have to, sometimes you might not. So we'll see. Here, this has a maximum. You might expect that, well, why doesn't it have a minimum? Why doesn't this have a minimum? What could you do to L and W? What could you do to L? Right, you can make L as small as you want and make W really long, right? What would that do to the area?
Decrease it.
And where would it go? That's right, you can make the area as small as you like, right? By making L really small and W really long, right? Okay, good. So you can make W really close to 50, L really close to 0, and the area gets really small. So I bring this up only to say that it makes no sense to talk about the minimum, right? So that whatever you get at the end, if you have to determine whether it's a max or a min, it's clearly referencing a maximum. All right. Okay. So what we want to do is we want to maximize A, and so we want to write A as a function of one letter. Right, so we want to write A as a function of, pick a letter,
B.
L or W.
W.
W, okay. Thank you, brother. It's a function of W. All right, and so that means that we need to solve for L in the constraint. Right? And so the constraint equation is the one that you must abide by. L and W are not free to be anything. They have to satisfy that equation. That constrains what L and W could be. 2L is equal to 100 minus 2W. L is equal to 50 minus W divided by 2. We will then substitute that in for L here, and A will be a function in terms of W by itself, and we are still maximizing that. And then it's over. Right? Once we have what A is in terms of W, then we can go ahead and do all of our calculus stuff. We'll then substitute into A. Right, so A is L times W, but we just found out that L is actually 50 minus W times W. And so A is a function of the width alone. It's 50W minus W squared. Now that we've written A as a function of W alone, then we maximize A using calc. Right? Here we could use algebra, as this is a quadratic, and use the vertex, but it's also a polynomial, and so it's pretty straightforward to go ahead and take this derivative, set it equal to 0 and solve. W is 25. L, well, if you want to find L, again, we were constrained. L and W had a relationship. 2L, well, let's go back to the easiest relationship. We'll recall that L is 50 minus W. So L is 50 minus W. We just found out that W is 25. L is also 25. My wife and I were having this conversation. I said, oh, you should build a square. You should build a square. A couple weeks later, she hadn't really gotten around to making the play area. She gets a raise. She says, honey, I get to go get more fencing. I have more money now. Right? So she goes and she gets 1,000 feet of fencing. She's like, what should I build now? What would I tell her? A square for sure. So a higher level analysis of this says that this, of course, what you build has nothing, the object you build has nothing to do with the amount of fencing. You should always build a square. Okay. Questions about that? I want to do the, what do they call this? I want to do the adjoint problem. This is the mathematical way. I want to do the adjoint problem. I'll take any questions about this. So let's highlight. So constrained optimization problems, that's what these are called. We'll do some general optimization problems in a moment. But you'll be given one function that you're trying to maximize or minimize, and then some constraint. And then you want to use the constraint to get one of the variables in terms of the other, substitute into the objective function, and then use calc. All right, that's the general game plan for constraint optimization. Let me go ahead and give you another constraint optimization problem. No, let's do the adjoint first. All right, so we're now in an alternate universe. Right? We're in an alternate universe, and so we don't have that much space. In this alternate universe, my daughter still wants a play area, and now we don't have that much space in the backyard. Okay, and so now in the backyard, the best we can do is give my daughter 100 feet squared of play area. That's what we're going to give her. And in this alternate universe, you know, I'm not teaching here. I'm the janitor here. Right? So now, you know, I still get paid a lot. I'm here, but I need to be very careful about how much money I spend, right? But I still want her to have that area. I still want her to have that area, but I need to make sure that I can spend the least amount of money possible. Right? I want to spend the least amount of money possible. So I say, okay, that's great, but when you go, you need to get the least amount of fencing possible to make that. And she said, how in the world am I going to do that? Right? So now we want to minimize the amount of material so that we have that. That's the adjoint problem, right? So then it's like we've switched the constraints, right? So notice what happened, that when we switch the constraints, then we're actually asking for a minimum and not a maximum, right? So now I'm going to minimize. I want the area to be 100, and I want to minimize the amount of material. And oh my goodness, when you all are making your products that you want to sell, and you got to put them in a box, right? And you know that you want the box to be big enough to hold your product, but you don't want to spend that much money on the box, right? And when you're rolling and dominating the world, you can imagine that Walmart really cares about this problem, because it's sending out tens of thousands of these, right? And so it is not so shocking. We'll do some other problems like this, that particularly places like Walmart and, oh my God, I don't even know if you all know Kroger. You all know Kroger? Kroger, okay. So I was about to say we have Giant Eagle here, right? But that, they hand out these cards for your benefit, right? And here at Giant Eagle, they're gangster. I mean, it's out of control. I tried to get into the fast checkout, the self-checkout, and they told I didn't have one of these cards. And they said, you have to go over there to talk to people, right? I have to, like at Kroger, you could at least go through the self-checkout and not have one of these cards, right? They want you to have one of these cards because they want to know what you're doing, right? They want to know everything that you're doing because they are collecting all of this data. Walmart has the largest database on people in the world outside of the Pentagon, right? And every time you buy something, no, that's crazy, right? Every time you buy something, right, they keep that information for 2 years. For 2 years, right? Because they're always trying to maximize, minimize, find the right price, right? So it matters that you get peanut butter every Wednesday to them, roughly every Wednesday or Thursday. That matters to them because then they know to give you a coupon on jelly. And that matters, right? And particularly that matters not just for you. This concept was, created by casinos where you are doing something over and over and over again, right? So that may not seem like a big deal. It's a big deal when you have 1 million customers, right? So that extra 3 or 4 cents for every 1 million customers means a lot of money, right? Just on that one product, right? So when you go to Walmart, something is $1. Something is $1.72 for a reason. Not 170, not 180. It's $1.72 for a particular reason, right? And that's because that's what the data says, right? And so over the last decade or so, data science has just gone ridiculous, right? Being able to think about these companies have all this data. And, I've been so blessed to be able to see this happen that 10 years ago, nothing was going on. And then all of a sudden, you see an industry just come out of nowhere because technology said, well, we can collect all this data. And then people are just like, well, what the hell are we going to do with it? Right. And then all of a sudden, people just start popping up and say, oh, I know what to do with it. 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 Right. And then all of a sudden, like these companies that just do nothing but just take data and just start doing stuff with it, make tons and tons of money. Right. And so what happened, that's not going to stop. Right. And so when I look at you, I see people who are just going to either dominate emerging industries or create new industries. Right. Out of solving the problems that come up because of how technology evolves. Right. So that in its basic sense starts here in this place where you have some constraints and then you're trying to maximize or minimize something, right? Questions about any of that? Comments? Okay. All right, so now, assuming that all of this stuff is made of the same stuff, then we can leave the price out of it and simply minimize the amount of material will label the same way, 2L, 2W, 2L plus 2W is now what we're trying to minimize. It's the total distance around. Again, we could multiply that by the price, but that would not change what the minimum is, right? I could say let's minimize the cost. My wife would go to Home Depot, says it costs $3 per foot, and then we would just multiply that by 3, and that would be the cost, and we would minimize that. But of course, we would just factor out the 3 and still solve the same problem. As you might expect, for some problems, people want the top of a box to be a different material than the sides, right? That's just adds more complexity to the problem, but the problem doesn't change. So we'll do one of those maybe too. We know the game plan now. What do we do?
All right, A is a function.
We're writing P as a function of one letter. Pick a letter.
L.
L. W is equal to 100 over L. Right? The goal, of course, now is we're going to take this, plug that in here for W. P will then be a function of L only, and then it's calculus time. I'm going to leave that to you initially to try and solve that. We did this function already. We did x plus 1 over x a couple of days ago. That's what we're trying to maximize. Remember, the function of L is 2L plus 200 over L. We'll take a derivative. 2 minus 200 over L squared. We need that to be 0. Here, just go to Algebra Town, solving for L. Goes minus 2, we subtract 2 on both sides, or we could have added this to both sides. We'll cross multiply, 200 is equal to 2L squared. L squared is 100. That means L is or 10, or L is negative 10. Context of the problem says that I'm looking for L to be a positive number, and so this is not feasible given the context of the problem. So L is 10. This relationship between L and W, L was 100 over W. It's 100 over 10. That was also 10. I'm sorry.
We found L, we're solving for W.
Oh, W, that's right. It's W. W is 100 over L. Again, the square. We should go the square. Questions on that? I'll tell you how I could say this crazily. It's really, so let's just reorient the problem before I go to the next slide. This okay? Find numbers x and y with, wait, let's write it this way. Whose sum is 50 and product is a maximum. Of course, the mathematician says that we already did this problem. The sum is 50. We're trying to maximize x times y. Answer? 25 and 25 is the exact same problem we did, just the story was different. So don't be intimidated by the story. I can ask all sorts of questions all sorts of ways. Okay? Questions about this? So I've only written this one because it's the same story. I guess we'll write that. So it's the same story. Well, it's the same problem, just a different story. Same problem, different story. So same problem as the first one we did. And so I could say find, the other way of saying this problem, of course, is find two numbers whose product is 100, whose sum is a minimum. That's the same problem. Okay, excellent. Let's do some, I think I pulled up a PDF of some problems. Maximizing, minimizing. Let's see here. Oh, so yeah, so 1 and 2 is that. Classic problem here. This one. Taught all over the place. This story's been told so many different ways. Sometimes you got some cow hanging out by the river, and you want to fence the cow in. What are the dimensions to do that? A rancher wants to enclose a rectangular area next to a river using 1,200 feet of fencing. She does not need fencing for the side next to the river. What are the dimensions of the rectangle that maximize the area? And what is the maximum area? So draw a picture. Oh, I should use blue, right? There's the river. There's your rectangle. this.
Do you actually have a decimal value there?
I have no idea. I have no. So. One of the most important steps, of course, is the label. Label the dimensions, L and W, or X and Y, however you want to do it. Clear constraint, 1,200 yards, they're using yards. 2L plus W is equal to 1,200. And we're trying to maximize the area, which is L times W. We'll run through this super quick. Again, this will give us a quadratic. Seems nice to solve for L in this case. I'm sorry, solve for W in this case.
Oh, you wrote 2 W's.
Put W twice.
Oh, I'm sorry. W's 1,200 minus L. 2L. Thank you. Yes.
If we drew it in a diagram, do I change it to?
Let's see it. Yeah, you do it that way, and we'll do it this way. See if we get the same thing. Yeah, we'll see. So A equals L times W, which is L times 1,200 minus 2L. 1,200L minus 2L squared. The derivative is 1,200 minus 4L. Decimal, yes, no? 0. L is 300. W is 1,200 minus 2L. That's now 1,200 minus 2 times 300, right? 600? Question? Did we get the same thing?
I did this, and so I had 2W plus L equals 1,200. But I'm thinking that's not
Well, let's see what you did. The formulation should not really. So you drew what?
So I drew it like the long way, and then like when the shortest side.
Like this?
Yeah.
Okay. And you called this?
I called that out, and I called the bottom down.
Oh, so you did this?
Yeah.
Oh, this should not. And so what did you end up writing?
I had 2W. Oh, no, I had the W being the twice.
Okay.
And so I had 2W plus L equals 1,200, and A equals L times W.
So this was W and this was W?
Yeah, kind of like that. But
Okay.
On the side.
Okay.
And then I solved for L.
So 2W plus
L equals 1,200.
equals 1,200. Go ahead.
And then I said L equals 1,200 minus 2W.
Okay.
And then I put L into the area equation.
Yes.
So I had 1,200 minus 2W multiplied by W again.
1,200 minus 2W.
All multiplied by W.
Yeah.
So I got 1200 W minus 2W to the power 3.
To what power?
Oh, there it is. Never mind. I got it.
No. Yeah, so we're just using different letters, right?
Yeah.
So she should get the same answer we get. Right? Because, again, we don't care about the letters. Her equation is the same as ours, right? Okay, good. All right, so got a soda can. $12 ounces. Whew. Need more sleep. 12 ounces. I'll look that up. 350 cubic centimeters. This is equivalent to 354.88 cubic centimeters. We'll just make it 350. 350 centimeters cubed. That's what a unit is that?
Volume.
That's volume. The volume must be 350 centimeters cubed. The volume must be that. So we made this tremendously amazing drink, Sam's juice. Right? So we made Sam's juice. What's in Sam's juice? I'm afraid to ask. Oh my goodness. What are the ingredients? We got some what? Tears? Let's do it. So it's a little bit of tears. What else? Ibuprofen. We mix that in. Okay. Water. Okay. What is it? Liquid stress. Okay. Okay. You all act like you need to throw some tequila in there. All right. So okay. So maybe that's the adult version, right? Okay. Excellent. All right. So, do you all get paid to do this? No. Okay. So we're trying to make a lot of money on this. Okay. So we want to minimize the amount of material, right? We want nice material, but we want to minimize it. So, I'm going to minimize the amount of material. Of course, that's the street version, of course. And this is the other thing. This is why you're going to get paid so much money, because, oh my goodness, somebody from the street, this is why I keep talking about the street version. Somebody from the street is going to come to you as an expert and say, yo, I have this problem. Here's this cash. Solve it. Right? That's what everyone's going to be doing to you, right? And so they're going to give you the street version, and they're going to rely on you to do the translation. They're actually asking about what thing? The surface area. Right? When they say, yeah, I need to minimize the amount of material, and they're not going to use the word minimize. They're going to say, I want to save the most money. That's what they're going to say, right? And then you're going to have to translate that to me. I want to minimize the amount of material, which means I want to minimize the surface area, right? So we want to minimize the surface area. We know from the context of this that we're talking about two letters here. What are they? R and H, right? So it's R here, the height H, right? And they play the role analogously to X and Y and L and W in the other problems, right? Go ahead and try and formulate this optimized constraint problem, right? In terms of R and H. And then let's try and roll through it. We need the surface area of a cylinder. That would be the area up top plus the area here. That's the area up top, the area down bottom. So that's pi r squared, right? And there are two of them. And then you can make a rectangle out of the rest of this if you want. So you would do that, and so what would the circumference would then be? What? 2 pi r, and then the height, that's the that's the height, and then the width would be h, right? So it's this. Is that okay? So either you memorize that or you just derive it every time. So all we're doing is this. We have two circles. So you have two circles plus another circle plus that area, right? That's how you get the surface area of a cylinder, right? So you take the top off, the bottom off, those two areas, that's two circles. And then when you unfurl this, you get something that's h by the circumference, right? So it's like 2 pi r by h.
They use the radius for the height of the pressure.
No, they didn't. But they, they did not. And so, what's the volume?
350.
That is 350, but how do we write it in terms of r and h?
R.
R squared H.
Pi r squared h, right? Oh, where'd you go? Oh, it's just down some. All right, so we want to minimize this. So we'll call this we'll call that S, subject to the constraint that the volume is 350. Again, that's the volume in cubic centimeters of roughly of a 12-ounce can. And so pi r squared h is the volume in terms of the radius and the height, and that is 350. And so it's the same program that we've been having, except we just got to do some more algebra stuff. Now we were very lax in solving for one of the variables. Here it's better to solve for which one of these variables? It's better to solve for h, right? Because if we solve for r, we would need to do what? Take a square root, and we know at some point we plan on taking a derivative, so we could do it that way, but if we know where we're headed, it's probably better to do this. Again, that's just a choice. Right. H is then 350 over pi r squared, and then, of course, all the h's get turned into r's. And then we'll have the surface area in terms of r only, and then we go to derivative town. S is equal to 2 pi r squared plus 2 pi r h. We just decided to replace h with its relationship to r that was given to us through a constraint on the volume. H is now 350 over pi r squared. And then we'll see that this is no different from one of the problems we just did earlier, except now we have this constant floating around. 2 pi r squared plus, looks like the pi's cancel. Is that 700? 700 over r?
Yeah.
Okay. We'll take a derivative, set it equal to 0, and solve. Super ugly number. Yeah. I mean, once we saw pi, we knew it was over. Right? Pi was never going to be nice for us. Pi is transcendental. Well, more importantly, not more importantly, but more tangibly, pi is irrational, so it was never going to be a nice number. S of r is equal to 2 pi r squared plus 700 over r, and S prime of r, or ds dr, is equal to 4 pi r minus 700 over r squared. And then it's just all algebra at that point, getting r by itself. And so I'm tutoring Scholar tonight in Calc 3, and so he'll do stuff like this. And as we mentioned before, he doesn't have to reduce things back to one variable. He has methods that relate the function that we're trying to minimize as a function of two variables to the constraint function that is a function of two variables. Those two functions are related in a nice way. They get you the same thing. We'll put these on opposite sides of the equal sign in order to cross multiply. Of course, you could also just multiply by the common denominator, but I like cross multiplying. 4 pi r cubed equals 700. R cubed equals 700 over 4 pi. R is equal to the third root of 700 over 4 pi. So of course, if this is a homework problem, you might need to get this to a certain number of decimal places. If Jessica or I are grading this, you could leave it like that. You do want to go back and get H. The question is probably what should, as anybody, as the business person would want to know, she would want to know what should the dimensions be so that I can save the most money on making this can. And so of course we want to go back and get H. She would certainly want to know what the height of the can would be. Super ugly 2, H is 350 over pi r squared. So 350 over pi times this thing squared, right? The third root of 700 over 4 pi. Approximate as you need to. Questions there? Yes?
So, how again do we know that it's the minimum?
Oh, that's a great question. So the minimum as opposed to the maximum?
Yes, sir.
Right. So we could do all sorts of things to let's go here. The best way to see it would be this. So the question is, this is the surface area in terms of the radius. So this is saying a lot of things. This is saying, well, I could make the radius. So when the radius is really small, what happens? Right, it gets bigger, right? And when the radius is really large, it gets bigger, right? So that means that there's a minimum somewhere in between. Right. Questions on that? Say that again?
Will we be allowed to have calculators and stuff?
Oh, no. Yeah, these are all acceptable answers. Yeah. That's all, yeah. We know that you know how to use a calculator. So yeah, writing H and R as this is okay. Yeah. Other questions about this? Okay. Got a line. Y equals, let's do 2x plus 1. Oh, let's do 1 minus 2x. Let's do that. Let's do 4 minus 2x. I like 4 minus 2x. That line comes rolling down like this, negative slope. What's that point right there? 0, 4. This point.
2.
2 comma 0. Excellent. This point here. What's that point? 0, 0. Good. What point on this line is closest to the origin? What point on this line is closest to the origin? So there's some point here that we don't know. X, Y, whose distance is the closest. So scholars at University of Pennsylvania taking an online class, Cap 3 over the summer. He's crazy, but he's also rich. So we are having great conversations about this 3 times a week. So he's like, so when you're doing these problems, how do you know that it's an optimization problem? And I'm just like, look, there's only but so many ways you could say largest, smallest, farthest, closest, right? There are only but so many ways you can use adjectives to describe something being the biggest or the smallest, right? And that's basically it: largest, smallest, farthest, closest, biggest. Okay, so this is an optimization problem, right? That's constrained. What's the constraint? You have to be on the line. What are you trying to minimize? The distance. The distance. Okay. Right. So by the way, the picture is important, right? So you're trying to minimize the distance, and so the distance is equal to what? The square root of x minus 0 squared plus y minus 0 squared. It's that we're trying to minimize. Anybody want to do this without calculus?
You just find a midpoint.
You think it's the midpoint?
I think so.
Think it's the midpoint? Interesting. Okay. So you're saying it's
1,
1 comma 2? The claimant said it's 1 comma 2.
2.
Other? Let's see what happens. We're trying to minimize this, x squared plus y squared with the square root. We're going to make a remark about minimizing the square root is the same thing as just minimizing the thing inside the square root. We don't need the square root in order to do this. Okay. So we can actually make our function x squared plus y squared, right? So we can call it capital E is x squared plus y squared without the square root. Is that okay? And so we want to minimize x squared plus y squared subject to the constraint y is equal to 4 minus 2x. And so this is not so much of a problem because in terms of our steps, we know exactly what to do. We're going to plug in y, right? 4x minus 2x, 4 minus 2x there, and then the distance is a function of x only. We'll take a derivative and solve. We know the steps here. And therefore, it's about just formulating this problem. Yes?
Why did I use the square root here?
Oh, that's a great question. Thank you. So if I look at the square root of u, right? So the square root of x looks like this. Square root of x looks like that, right? And so the minimum of the square root is the same place where the minimum of x of the inside is, right? So wherever this looks weird to me right now. Wherever the square root of x, well, that's right, f of x. Wherever the square root of x is smallest, is the same place where f of x is smallest. And that's also for being largest. That if I look at the square root of f of x and say, well, where is that going to be the smallest value? It's exactly the same place where f of x is the smallest value. So minimizing the square root of something is going to be at the same place. It's not going to be the same value, but at the same place where f of x is the smallest. That makes sense? So we can demonstrate this in the following way. So if I have the square root of f of x, right, and I want to make that the smallest, it's f of x to the 1/2 power, right? And so if I'm looking for local maximum or minimum values, I would take the derivative. What's the derivative of this? Right, so the derivative of this is 1/2 f of x to the negative 1/2 times f prime of x, right? This is equal to f prime of x over 2 times the square root of f of x, right? Is that okay? I would want this to be 0. And if I want this to be 0, what has to be 0? The numerator. Right? So this is 0 whenever the derivative is equal to 0, which kind of means that I should have never been paying attention to this to begin with. That I never needed the square root. That the place where this has local maximum or minimum values is the same place where the function itself has local maximum or minimum values. Right? So you can keep the square root, right? You can keep the square root, but when you solve the derivative equal to 0, it's the same place where the original function has a derivative equal to 0. So just pay attention to the original function. Right, so that's the mathematical way, and this is one of the rare times, and I could be wrong, where the mathematical way was way better than my silly explanation with words, right? So, but the street version is that, again, the square root does not impact how the place where you're the largest or the place where you're the smallest. If you're biggest for f at 7, then you're biggest for the square root of f still at 7. If the smallest value of f is at 4, the smallest value of the square root of f is still at 4, right? Because the square root doesn't impact the size, because it's because it's increasing. Go ahead.
It's just the square root.
Oh, it's for any increasing function, right? So it's because the square root's increasing, it preserves largeness, right? So if the square root function is going up, then if your function is getting bigger, the square root gets bigger. So it preserves the order of things, right? So that's true for the square root, that's true for the cube root, that's true for any root because they're all increasing, right? And that's true for the natural log. That's true for, so if you wanted to maximize the natural log of f of x, you should just look at f of x. Right? Excellent question, please.
For what you just mentioned, does the root have to be over the entire function?
Oh, it does. Yeah, so thank you. These are fantastic questions. So the function has to be completely inside the increasing function. Yeah. Yeah, absolutely. So looks like we just said a theorem, and oh my goodness, it just screams like it should be extra credit, right? I have no idea how to do this, but let's see. It seems like we have the proof, but let's just see if this is true. I don't even know if this is true. So here's a claim. If h of x is increasing, let h and f all be nice and differentiable. If h of x is increasing, then the critical numbers for g of x equal to h of f of x are, well, are at least the critical numbers for f. And so we'll do an example. So for instance, here's an example. So this example should help us for any particular h. You should be able to follow this proof for any h in general. If we use the natural log of x, if h of x is equal to the natural log of x, then g of x is equal to the natural log of f of x. I think this is going to be pretty easy. So I need the critical numbers of g. I'm assuming that the critical, I'm trying to show that when I look at the derivative of g and set it equal to 0, then that's going to be at least all the places where the derivative of f is equal to 0. Right? So what's g prime? 1 over f of x times f prime of x, and I'm setting that equal to 0, right? And so the question is, when I solve this, do I at least get all the places where the derivative is 0 of f? This implies that what? F prime of x is 0, right? And the answer to that is yes. Now you may get more, but you at least get those, right? And so that shouldn't change if I give you g, because if I call g h of f of x, we know what the chain rule says, and I think it comes pretty easily. Right? So the question is, how are you going to write that in words? Right? How are you going to write that in words? Right? So that the critical numbers for g are at least the critical numbers for f. Right? So for the extra credit, change natural log, leave it as h, use the chain rule formula, and then write something that makes sense. Even or odd? You started this. Oh yeah, you started this. Odd. Good. 3. All right, so that's just going to be about how you write it out. Extra credit, 3 points.
What was the question again?
So the question is that when, so I'll say it in words. So well, here's the question. So let me translate. So that when you look at the derivative of g, why is that going to include all of the places where the derivative of f is equal to 0? And so that informs us that if I'm trying to maximize g, it really is very much tied to the maximum of f. Right? And now I think I'm ready to say that they're exactly the same place. That the derivative of g and the derivative of f are 0 in exactly the same place. Right? And so when you're doing this, you better use this somewhere. Right? And so, I'm sorry. So I'm moving this out of the way. The critical numbers of g are at the critical numbers of f. The critical numbers of g are the critical numbers of f. We'll make this worth 5. I just realized something. So it's not at least, they're exactly the same. Okay, great. Excellent, excellent, excellent questions. I love intelligent people. All right. So now this was all to say the following. This is all to say now that, where is it? I think it's on the previous page now. Here is our problem. Then we wanted to minimize x squared plus y squared subject to y equals 4 minus 2x. Minimize. All right, we're off the function town. All right, so here's our function now. Capital D of x equals that. Just replacing.
trying to find the distance, right?
Say it again.
We're trying to find the minimum distance.
We're trying to find the minimum distance. That's right. Closest means minimize the distance. Closest means minimize the distance. The derivative of x squared, 2x. The derivative of 4 minus 2x squared. 2 times 4 minus 2x to the first times negative 2. Let's solve for x. 1 comma 2, you say. 1 comma 2.
That's right.
Oh, that's not right? Okay. We could have just squared d out completely and then done it. But we have the chain rule. Why not use it? Right. That equation for d prime is completely linear. We'll find what x is. We'll answer this question in all the ways I could ask it, right? What point on the line is closest to the point? What is that distance? You know, what's the minimum distance between the point and the that point in the line? All these sorts of things. All right, so let's run 2x. That's minus 4, right? Minus 16. Minus 4 plus 8x, is that right? Equals 0? Okay. That's a funky number, right?
It's a fraction.
So 10x, I'm sorry, that implies that 10x minus 16 is equal to 0. X is equal to 16 over 10. 8 over 5? What you got? Wow. Okay. 8 over 5, what's y?
4 over 5.
4 over 5. Y is 4 minus 2x. We just found out what x was. Equals 4 minus 16 over 5. 20 over 5 minus 16 over 5 is 4 over 5. The answer is what? 8 over 5, comma, 4 over 5. What did you say? You can find it. You just plug it into the distance formula. Square root of 8 over 5 squared plus 4 over 5 squared. Any way to make sense of this? Is there anything special about that point? So line. And so then that is what? Where is that? Is it above or below y equals x?
1.6 comma 1.8.
Say it again?
It's 1.6 comma 0.8.
1.6 comma 0.8. So that's like, so wait, this is 2?
Yeah.
Okay, so that's 2, this is 4. So 80% of the way, something like that. But it's 0.8, so okay. Maybe something like that. I don't like it. This is so off scale, right?
You can graph it on
I think we should, yeah. So then we graph it. Y equals 4 minus 2x, and then we're going to graph this point. Okay. I think I want to probably change these axes, right? I think we should just do 0 to 3, right? 0 to 3. I guess we could do 4. I'm sorry? It was just to the origin. I mean, you want to do -1? I mean, you can do that. 0 to 3. And then what's this other point we got? What's the point that we just got?
1.6 comma 0.8.
1.6, comma 0.8 is there. All right, so what line is that? You know what that line? What is that line? That connects the origin to that?
The distance itself?
No, just the line. What's that line?
1/2.
Y equals
Slope is 1.
the slope is 1/2, and it goes to the origin. Right. Scale is way off, right? So the slope of I think we probably want a box, right? So if we do negative 5 to 5, and then this is negative 5 to 5. And then we'll put the functions back in. Yeah. 4 minus 2x. And then y equals 1 over 2x. Like that. Is that okay?
You can minimize the keyboard if you want.
Oh, you want to do that? You just want to look at that? Okay. So we have issues in terms of scale. These lines, I guess we could, it's actually easier to see. I can't see it on my computer. Perpendicular. Lines are perpendicular. You don't see it?
Is that what you're
Would be negative 1.
No?
Is that what
Think it's at an angle? But are these two lines perpendicular?
No.
Oh, this is good.
Oh,
Should be.
no, they should.
Wait, no, it shouldn't be. No, wait, yes, it should.
I'm ready to give everybody C's. I'm ready to do it. I'm ready to do it. Again, I got beach property in Iowa I need to sell you for $15 per square foot. This is ridiculous, right? So you look at the two functions, and I don't give a damn what the graph looks like. Right? Yeah, they are perpendicular, right? So this is why I said that there's something wrong with the programmer, right? There's something wrong with the programmer. Okay. Now, why are these perpendicular?
Because one slope is the negative.
The slopes are negative reciprocals, right? The slopes are negative reciprocals. So, good. So, is that coincidence? This is actually how we define the distance from a point to a line. That's how we define it. It's the perpendicular projection of that point on the line. Right? That's the definition. From this perspective, it looks perpendicular from this angle all the way over here, where my angle's like this. Right? Right. That's right. So the question that's what's interesting, right? So what I tried to make a square, the square didn't work. So what box would make this look perpendicular? I just made it. This box is a square. That's why I made it.
I'm talking about like.
No, go ahead. No, think about it.
The
Yeah.
boxes themselves aren't square, so.
Right. Wait, what are they then? They're not square.
They're like rectangular.
Are they? 1, 2, 3, 4. I think it's 4 by 4.
The units, yeah, but
Yeah,
like
but
the
it
actual
appears as rectangle.
boxes.
The what?
The distortion.
The distortion. Right. Yeah. So if you're saying if I got rid of this,
If you zoom out, you can.
yeah. So if I just move this over, no. That looks better? Okay, yeah, okay. So that's an interesting problem to think about. Right. But the remark is that the answer to that question is probably just going to be this, right? That's the point. So you could have found it without calculus by understanding that this is probably a right angle, right? And then you could do some things there, right? So, and maybe that's just true for this one, but yeah. All right, I don't know the answer to that. I don't know. You want to make it extra credit? Right. So the question is it always going to be, right? So if I did this line, right? If I did this, right? Is that still true? Right? If I give you some other line, is it always going to be the perpendicular? All right, let's do it. Consider.
We're working with math, like not with like h f x and never mind.
Say it again.
So when we prove this, I know we can't use math. Like we use the same follow-ups. Like f of x is g of x, and then like.
I think I see what you're saying. Yes. So yeah, let's formulate what we're saying. So consider y equals negative mx plus b, where m is positive and b is positive. So we'll just do a line that's going through the first quadrant. So that's a line with negative slope, right? So the question is that the point on this line closest to the origin is the point on the line y equals what?
Negative 1 over
I already have the negative. 1 over mx. Yeah.
10 points.
Even or odd? Even? Whew! That's why you don't yell out a number, because then it, yeah.
The average of the
The average of the even and odd? Then there's no reason to say even or odd, right? Well, yeah, I like 8 points for sure. Let's go ahead and do that. I'm excited about that. And it may be easy to write. I don't know, right? So what does this require? This requires that you look very carefully at what you did when I had the numbers in there and do the same thing, but keeping track of the letters, right? So you're going to do the same thing with the letters, come down to a point like you had before, and then that point, it looks like it's going to be zero. I'm sorry, it's going to be something that has slope 1 over m when you connect the origin to that point. Right? So I'm excited. That's something you definitely want to bring to me so I can look over, make sure it's being written correctly. Wow, that's fantastic. Questions about what I'm asking, right? So again, I think this should mimic this roughly, this argument with just a bunch of letters. Go ahead. Okay.
We should make the extra credit like an exponential function. So like up to like the second one, it like
This goes higher. I don't have that much of a problem with extra credit. Yeah, no, our problem's not that big. Yeah. So the problems do get harder though. Yeah. Okay, we'll end with one more problem, classic problem. Where is this thing? I think it's here.
Closest to the origin on the line has a slope 1 over m.
we already finished that.
All right. A man on an island 16 miles north of a straight shoreline must reach a point 30 miles east of the closest point on the shore to the island. If he can row at a speed of 3 miles per hour and jog at a speed of 5 miles per hour, where should he land on the shore in order to reach his destination as soon as possible? So I've usually phrased this problem in other ways, right? So you've got here's the water. That's also the shoreline. You're out here in the water, right? You're out here. They say he's on an island.
How's he gonna drop there?
What'd you say? This is the water. Out here's the water. Right? And so the question is, this person is going to, I put this in the wrong place. This person is going to swim somewhere to the shoreline in a straight line. And then run the rest of the way. So swim and then run to get home to have lunch or whatever. Okay. The question is, where should this be? Where should that be? So you're out in the water. There's an emergency at home. Someone's screaming like, get home, get home, get home. Right? You know how fast you swim. You know how fast you run. Should you just swim straight and then start running? Should you just swim the whole way? Or is it somewhere in between? Go ahead. Oh, I will in just a moment. Right? So, but when we have this type of problem, again, high-level people, you know, when you're serving the layman person who comes and just says, I need to know how to solve this problem, then you need to start to ask yourself, well, wait, what does this all depend on? Right? And obviously, if this person can swim 3,000 miles per hour, then that person should just go, and they can run 2 miles per hour. That person should just swim the whole way. And the reason why I bring up these extremes is because it gives you an idea of what the possibilities are, right? So if a person can run much faster than they can swim, maybe they just want to get to here as quickly as possible and then run the whole way, right? So this has something to do with the speeds of swimming and running respectively, right? Which is precisely why they give you those. And why that's a real extra credit problem to find out what that relationship is in terms of X, right? So this distance is 16. This distance is 30. Now, that requires just the smallest hint of subtlety. They said that this person is going to swim, this person is currently located 16 miles from the closest point, which is 30 miles. This is the closest point, right? So any other place is longer, right? Because any other place on here would be the hypotenuse of a right triangle, which of course is the longest side, right? So the vertical place is the closest point, right? Because if I dared think that any other place was closer, that would be false, because you could make a triangle, that being a right triangle. So that's why the closest distance is always just a straight line. So that's X, and that's it. What are we trying to minimize? The time. Oh, we obviously need that. So he can row, or in our case, for my silly story, you can swim 3 miles per hour. So in this area, you can swim at 3 miles per hour, and when you're on the shore finally, you can run at 5 miles per hour. We'll at least formulate this function before we take any derivatives, and we can start there, taking derivatives of this tomorrow. We're trying to minimize time. Time we know. How does it relate to distance and speed? Time is distance divided by the speed, right? So the total time that you spend is
distance spent.
the total time that you spend is the total time you spend in the water plus the total time you spend running. Right? Total time equals time in water plus the time running. We'll get a coordinate system together. This is due to Descartes, the Cartesian coordinate system. I get to decide when we coordinate something. I don't even think that's a word. When we put something in a coordinate system, we get to determine what the origin is. I would like the place on the shore that's 30 miles away from our destination to be the origin. And that makes sense, hopefully. That I'm going to call this, this is the point 16, 0, 16, right? That's where you start. And we're looking for this coordinate x on the x-axis, right? I put this in a coordinate system because this helps us get the functions a little bit better. We're talking about traveling this distance in the water, and in this case, the water represents the first quadrant. And then I want to travel this distance on land. On land is now on the x-axis. Please.
I thought you said it was quicker to go straight down.
No, sometimes it is. I said that if I was running way faster than I was swimming, then I want to spend more time running, which means that I just need to get to the shore as quickly as possible. Right? But that depends on the relationship between swimming. If I can swim way fast, if I'm Michael Phelps, I'm swimming the whole way. Right? So that's right. Yeah, exactly. So it depends on the relationship between how fast you run versus how fast you swim. Does that make sense? Yeah. So in some instances, you might just want to swim the whole way. What's the distance here? Right, so I have 1.016, and what's this point here? X 0 for sure. Okay. Square root of x squared, absolutely, plus 16 squared. For sure. This distance here? 30 minus x for sure. This distance is x. The whole distance is 30. The remaining distance is 30 minus x. The time in the first quadrant, or in this case, the time in the water, is the distance in the water, which is the square root of x squared plus 256, divided by the speed in the water.
3 miles.
Was it 3? Yeah.
I think so.
The time on land, which means the time on the x-axis, 30 minus x over 5. And we want to minimize the sum. Right. So what makes this problem supposedly harder is that the problems we've done today have usually their difficulty have come in different places, right? Either it's been, I tell you this ridiculous story, and it's like, wait, I need to navigate through all these words. What is he trying to say? What is he hiding, right? And then you finally figure out what we're trying to do, and then its derivative, the calculus is easy. Or I give you some simple story, and it was easy, and then all of a sudden this function is ridiculous, and now we got to take the derivative of it and figure out these things. Here, this has a little bit of both, right? Where the story is like crazy, you got to put it all together, and then this derivative is not going to be trivial either, right? So we'll start here next time. We'll add those two, take the derivative of it, and find the place that that person should swim to so that they can run there the fastest.
Oh my gosh.